let us look at a couple of examples to appreciate pumping lemma. Consider this language a power n b power m, where n comma m is at least 1. We know that this one is regular because one can construct a finite automaton. We read the first a and read n minus 1 a's, read the first b and read m minus 1 b's. And we also know that one can come up with a regular expression for this, or it could be a star a followed by b star b. Now if you look at this, it only says read so many a's followed by so many b's, and you don't need to remember the number of a's. Similarly, number of b's. It is some integer n, some integer m. Look at this language, which is closely related to this. It says a power n, b power n, where n greater than or equal to 1. So what this says is the number of a's read one should remember, so that one can match with the number of b's, and their count must be same. But intuitively we know we can only say so many a's have been read, but the exact count cannot be output by finite automaton, or it cannot be remembered by finite automaton. Therefore, when we start reading b's, we cannot match with number of a's read. So with this intuition, we think this is a candidate for non-regular language. Let's use this and try showing it is indeed non-regular. So there exists L. So this is our language for all n. And if you look at the description, L is regular implies there exists n, that n was representing the minimum number of states in the underlying finite automaton. Over here it could be some constant that says you choose any n, there exists w, and length of w is related to this. So the first task is the following. We need to choose w carefully such that length of w is at least n. So what we will do, let me choose w to be a power n, b power n. Now what is the length of this? Length of this is 2n, which is greater than or equal to n. So we see that the condition is satisfied. Next, it says you come up with any decomposition respecting this constraint. So fix this a power n, b power n. You come up with any decomposition for all u, for all v, for all z, such that uv is at most n and v is at least 1. So if you look for a decomposition respecting this constraint, so it is clear that uv is fully contained in this part and z is rest of them. It may be b's or a part of a's followed by part of b's, part of a followed by the entire b. Correct? But one thing is clear, both u and v are only in this part. U could be empty, but v must be at least 1. Okay? That's all the condition says. And it is any decomposition. So I cannot assume, one should not assume that V is A and U is something like this and at most n minus 1. No assumption on this part because it could be any decomposition. But one thing is clear, V is in this part. So let's assume cardinality of V is K, which means K is. And this implies that UV is at most N, which means this one is cardinality of V is K, which means cardinality of U is at most N minus K. Correct? Now, we said you come up with any decomposition respecting this constraint, then go to this. The next one says, so now if you look at W, W can be written as A to the power N minus K and A to the power K followed by B power N. Okay, it is some K and the remaining part is this. So I am rewriting this as like this. Okay. Now it says there exists I. Now for this string, assuming V is this and U is A power N minus K, Z is this, it says there exists I. So you have the control with I. Let me choose I to be 0. If you choose I to be 0, what happens? W is A power N minus K and it says I greater than or equal to 0 and U V power I is at not in L. So which means W can be rewritten as A power N minus K, A power K to the power I followed by B power N. And this implies that A power N minus K, this part is 0 times B power N. And remember, K is at least 1 because V is at least 1. So K is at least 1. And it's clear that A power N minus K times B power N is not part of L. So now for this W, for this I, we have satisfied the premise of this statement. This implies that L2 is non-regular. So we have control over W, we have control over I. And for this W, you come up with any decomposition and choose one I for which we see you get a string which is not an L. One can also do this. For example, when we know W is A power N minus K, A power K times B power N, choose I to be say 2. If you choose I to be 2, then we get A power N minus K and AK square times B power N. So what we get is A power N plus K times B power N. Remember, K is at least 1. This implies that this string is not in L, because this will be A power N plus 1 and at least n plus 1 times this. Okay. So do not choose I equals 1. If you choose I equals 1, what will happen? You will not get a contradiction. You will get a power n minus k times a power k times b power n, but this one belongs to n. But what we want is, we want to choose one I such that u v power I z is not in n. So one has to carefully choose I, for which we get the true value for the premise of this statement. Since we satisfy the premise of this statement, conclusion follows. Conclusion says L2 is non-regular. Most importantly, no assumption about the decomposition part. We only observe that uv is at most n, therefore v must be contained in this part. Okay. So for the same question, a power n, b power n, one can also attempt a proof using some other w. So let me choose w to be a power n by 2, b power n by 2. Now length of w is at least n. Now length of this w is n. That constraint is satisfied. Next it says come up with any decomposition. So when we focus on a power n by 2, b power n by 2, now constraint says uv is at most n, which means now one has to look at possibilities, and it may be the case that v is in a part, which means u is also contained in a, or v in b, which means to the left of it it is a. I am only giving you example because one has to prove for any decomposition. For example, we take say n to be 4, then we have AA followed by BB. Fine. Now one case I can say this is U, this is V, this is Z. And another case is, one can say this part is U, this part is V, this part is Z. Or we can say this part is V, this part is this part is U, and this one is Z. Okay, so there are three cases. V is just containing A's, and V contains B's, and V contains AB. Correctly, yeah? Because V is at least 1. Accordingly, to its left you get U, to its right you get Z, and we do not know anything about U and Z. You only know about V. So one has to fix V, or one has to look at possible values for V. Accordingly, you get to see the picture for U and Z. Okay, so in general, case 1, V contains A's. Okay, only A's. So in this case, you get to see that we do not know how many it is. So which means it is some k, a power k. To its left it is U, which means it is a power n by 2 minus k. times b power n by 2, and k is at least 1. It contains only a's, some number, because it says any decomposition. And with respect to case 1, in any decomposition, which means we do not know whether it is 1a or 10 a's, 100 a's, we say a power k and the rest. Now, for this case, you choose I to be 0 or I equals 2. You see that for say I equals 0, we get a power n by 2 minus k times b power n by 2. Since k is at least 1, this one is not in L. On the similar line, look at case 2. In this case, V contains only V's, so which means you get something like b power k, and to its left it is u, to its right it is z. So z will be the rest, and it will be b power n by 2 minus k, and to its left it is u, it is a power n by 2. Okay. Now here again choose I to be 0, we get a contradiction, a power n by 2, b power n by 2 minus k, which is not in L since k is at least 1. Now look at case 3. In case 3, V has AB in it, so which means you get to see that V will be like some number of A's followed by some number of B's, and rest all this side. So let me say this one is some k1, this one is k2, and k is k1 plus k2. Because it contains both A and B, so we clearly know it will be at least 2, because it will have at least one A and at least one B over here. Okay. So before this it can have some number of A's, after this it can have some number of B's. So this part is clear. So to its left it is U, that will have all A's. To its right it is Z, that will have all B's. So this is my U and this is my Z. Okay, so we clearly see this. So a power n by 2 minus k1 times a power k1 times b power k2 times b power n by 2 minus k2. So remember, it has a and b in it, which means k1 is at least 1, k2 is at least 1, therefore k is at least 2 in this case. Here again choose I to be 0, which means this part will disappear. So we get to see that a power n by 2 minus k1 times b power n by 2 minus k2. Okay. So now you get to notice this carefully. So it says there exists I, and we take out this part completely, and this is our V, right? This is our V. What we are left with is a power n by 2 minus k1 times b power n by 2 minus k2. And we know this one is at least 1 and this one is at least 1. Fine. Now can we say for sure that this is not part of the language? Okay. Imagine the case where it is AB and you take it is exactly AB and you choose I to be 0, then what happens? This will have 1 less, even this will have 1 less, which means A to the power n by 2 minus 1 and B to the power n by 2 minus 1, and it is part of L. So one has to carefully look at this case. So what we will do, instead of this, let me choose I to be say 2. Now what will happen? A power n by 2 minus k1, this will be twice, correct? So which means A power k1 b power k2 followed by A power k1 b power k2 followed by b power n by 2 minus k2. This is our v. This becomes v square, which means AB, this pattern repeats. Now we see that this is clearly not in L, because this is not of the form A power n b power n. It says A power something, then AB followed by this. So this is clearly not in L. So for this case, do not choose I equals 0, because if k1 and k2 are 1, then we may not get a contradiction. Instead, choose I to be 2, then in between you see that AB, and but the string generated out of this is not in L. So in all three cases, we have established that there is a string which is not in L. This implies that L is non-regular. So this tells you that choose a string whose length is at least n. Now we have chosen a different string and respecting the constraint, and we were able to establish that it is non-regular.